So, welcome everyone to the course on advanced topics on the secondary ion mass spectrometry by Dr. Pawel Michalowski from the Institute of Microelectronics and Photonics in Warszaw. And I'll just leave the rest to you.
Thank you. So I'll first share the screen. And it worked well, so I guess it will work again. Okay, so can you see my presentation? Is it on?
Yes.
Yeah, okay, good. So I will start directly. As I was already introduced, I will be talking about secondary ion mass spectrometry characterization of thin films with nanometer and subnanometer depth resolution. At the beginning, maybe I will say a few words about me. So my past experience is listed down below. So basically, I studied my studies in Poland, in Poznań, in Adam Mickiewicz University. And then I moved to Sweden, far up north, to Umeå University, where I continue my master's study on physics department there, and obtained my master degree from both universities. So first, I got actually the Swedish master thesis and then Polish one. Then I moved to Germany, to Dresden, and joined Fraunhofer Center for Nanoelectronic Technologies. And that was in 2007. And that was actually the very important date for me because that's where I started to specialize in SIMS technique. From there, I moved back to Poznań, where I obtained my PhD degree in physics at the same university. And then starting from 2015, I joined Institute of Electronic Materials Technology, which was later on changed to join Łukasiewicz Research Network, newly founded in Poland, and form Institute of Microelectronics and Photonics. Currently in this institute, I'm a head of a department of structural analysis and materials characterizations. I'm also responsible for the SIMS tool, CAMECA IMS SC Ultra, that I will talk a little bit later on. And we also have various other advanced characterization technique available in our department. They are listed here. But as you can imagine, in my presentation, I will definitely focus on SIMS analysis and not any of these. So I'll just give a very brief introduction. I know that you are a SIMS user yourselves, so you definitely know the principles of the technique. So I'll just give a brief introduction, talk about some strengths and limitations, some enhancements of the tool itself that I'm using, and some procedures that I'm developing during my work. And the most important part of my talk will be examples, because I'm sure that this will give the best opportunity to actually appreciate what you can achieve with SIMS. But please note that in some cases the results are quite preliminary. They are not yet perfect, so some interpretation may vary with time. Okay, so let's start with the SIMS, secondary ion mass spectrometry. As I usually say during my talk, it has nothing to do with video games, because young people usually seeing SIMS assume it has something to do with video games. So no, I'm not getting paid for playing video games. But my job is fun nonetheless, as you will see soon. Okay, but usually when we say about the secondary ions, obviously we need some primary ions. So the technique is basically about the bombardment of the flat sample with primary ions, which cause a lot of various effects to occur. The first one is that these ions transfer its kinetic energy to the atoms from the sample, knock them out from their stationary position, transfer its parts of it energy to them, and these atoms start to move on their own. And they also collide with other atoms from the sample. They also transfer their energy to them and start their movement. in this case, the so-called collision cascade is generated. Obviously, one of the most basic phenomenon that occurs during the ion bombardment is the ion implantation. So we can find the primary ions somewhere in the sample artificially added there. So whenever we use some kind of a primary ion, we can't really detect these kind of atoms within the sample because we will simply introduce them during the analysis. The most important part of the most important phenomenon here is the sputtering and ionization. So part of this kinetic energy transfer to the atoms comes back to the near surface region, and then the sputtering effect may occur. So some particles may leave the sample, and a small part of them, usually below 1%, are additionally ionized, either positively or negatively. And these secondary ions undergo mass analysis, and we can then detect what type of atoms were in these samples. There are, however, other effects which make the interpretation a little bit difficult. The one is preferential sputtering. So it basically means that one type of atom may have a completely different probability to be sputtered from the sample, and thus we may form regions, as marked here, where we see a depletion of one type of an atom and agglomeration of the other. This does not represent the actual composition of the sample itself. It was caused by the experiment, so it has to be taken account that such an effect may hinder proper interpretation of the results. And the other effect, which is also making the life of a SIMS operator a little bit more difficult, is the mixing effect. So basically, when all these atoms start to move, will naturally push them down and bring some up, even though they were not present in these particular layers before. As you can see, and as you can imagine, the effect is asymmetrical. We definitely push down more atoms, mix them down, then bring them up. But both effects may occur, and it has to be taken into account to interpret the results properly. Basically, we use the technique for the to determine the elemental composition of the sample. In most cases, there is no or minimal information about chemical state. This is not always the true, particularly for TOF SIMS. In our case, I use the magnetic sector SIMS, and there many people usually assume that there is no information about chemical state. It's not always the true. I will show a few examples that actually there is some information about chemical state, but usually it's not the best technique for it. And more specifically, it's not good for analysis. For example, sometimes there are some people coming to me and asking, can you check in this sample whether this copper is in metallic state or +2 state? This cannot be done because ionization itself is artificially caused by the ion bombardment. So I will not get any information about it. How was it prior to the experiment? So this information is definitely lost. The most common application is to create depth profiles. So basically, when we start to sputter surface layers, we start to drill a crater in the samples. So we not only can check the elemental composition of a sample, but we can also see how this elemental composition changes as a function of depth, going through all the layers in the material. Many tools, including mine, also have position-sensitive detectors, and thus the lateral analysis can be done on the surface of the sample, and when combined with the depth profiling mode, a fully three-dimensional images can be obtained. So usually this is used to detect some kind of a stability of layers where there are sharp interfaces, or there are some kind of a mixing of these layers. Of course, the diffusion phenomenon is very well detected. And due to the excellent detection limits of SIMS technique, it's commonly used for dopant and contamination analysis. And what I would like to mark here is that typically it's not used for 2D materials. There are not so many publications that show such applications due to the thickness of these samples. But with some enhancements, it can be done with a very high precision. Okay. Now I would like to talk a little bit about the instrument that I use, about its main differences when compared to most of the other spectrometers. So the first difference is so-called extreme low impact energy technology. So while probably you know, in most cases, the impact energy can be decreased to like half a kiloelectronvolt, maybe quarter of kiloelectronvolt. In this case, the oxygen gun is not a duoplasmatron, which is commonly used for the gaseous sources. But here there is a radio frequency plasma generator, and it can decrease the impact energy of oxygen ions down to 60 eV. While in case of the cesium column, there is an additional floating voltage. So because typically when you start decreasing the acceleration voltage, you may get problems to obtain a good quality beam because of the electrostatic interactions. Primary ion will repel, and then the focusing of such a beam is very challenging. But in here, CAMECA used a very nice approach. So basically, instead of decreasing the acceleration voltage, I can keep it quite high, even more than 1 kV. But I apply additional floating voltage to the column itself, so I can gradually decelerate these ions, so that in the end, I can decrease the impact energy of these ions down to 90 eV. The other thing is that these two primary columns are completely separate, so they're optimized separately with the different angles, and that also gives the opportunity to tune the incident angle of the primary ion, especially for the cesium column, by applying this floating voltage. We can indirectly change the incident angle. As you will see, in many cases, I'm using the high incident angle well above 60 degrees from the normal, from the surface, which gives some new opportunities to perform analysis. And it's also important to emphasize that for such a low impact energies, the mixing effect that I mentioned before is practically eliminated. So these ions carry so little energy that they will not introduce any collision cascade. These atoms will not be mixed together. However, there is also one more additional enhancement in the tool. It is the case of the beam shape, because typically when you generate the beam, it is a Gaussian shaped beam, so the center of it is usually more intense than the edges. So if you think how such a beam is sputtering the material, it's quite obvious that from the middle part will sputter it a little bit faster than the edges. So the difference can be like 2-3 nanometers. And then obviously for such difference, when we want to consider two-dimensional materials like graphene, which is well below 1 nanometer, it's not good enough. This will blur our signals quite significantly. So in here, CAMECA is still generating the very same Gaussian-shaped beam, but then is projecting it onto square stencils made of tungsten, so that we choose only the middle part of the Gaussian beam, the most intense and most homogeneous part. So in the end, what is hitting the sample is a rectangular beam with still quite high intensity and very homogeneous. And if you think of it, such a beam can really sputter the material homogeneously, so you can really expect the sputtering process to be layer by layer. So with these two combinations, it can increase the the depth resolution significantly to values well below 1 nanometer. However, the problem with it is that usually when you apply so many changes like very low impact energy, you cut just a little bit of the beam, and then also you change the incident angle, as I mentioned, you lose a lot of the signal intensity. So for this, I made something that I call the dedicated SIMS procedures. So basically, when I compare it to standard procedures, so a standard procedure is typically optimized in such a way to maximize the total number of detected ions, as shown here. So this green cone represents the ions which are collected. But if you look at this, this is especially true for high incident angle bombardment, that various type of ions may have a very different spatial distribution, the sputtering directions. So if we want to consider other type of atoms, which I mark here in blue, as you can see, there is just a few of them that can be detected in such a way. So in my work, I spent a lot of time to create the dedicated procedures. So I don't optimize the total number of ions which are detected, but optimize these ions which are the most interesting ones. So in here, as I mark here, that this procedure is optimized in such a way to detect the blue types of atoms. And more importantly, I can also change the extraction parameters during the analysis, so I can switch from one type of atom to other whenever I need it. It's making a little bit more complicated analysis, but in this case, I'm gaining a lot of signals intensity. So then I don't need to worry about the noise of these signals, and I can really achieve the sub-nanometer depth resolution. And I will start with the very first example of such application of such a dedicated procedure. So this is one of my very first major achievement in SIMS, which I consider to be very, very good, is the analysis of the hexagonal boron nitride. So my idea was to actually reach the atomic depth resolution in this experiment. And I did it for the first. I used a very low impact energy and low density beam to probe just the top layer of hexagonal boron nitride. So I obtained some information from there. And then I used a very short pulse with a little bit higher energy, but with a very high incident angle. And this pulse is used to remove the top layer. This is causing the preferential breaking of the weak van der Waals bonds between the planes without causing any damage to the underlying layer. So I usually call it something like ionic exfoliation. I completely remove the topmost layer of the boron nitride and expose the second one. And then I can simply repeat the same process. I use a very low intensity, low energy beam to probe the second layer, obtain information about it. Then I use the same pulse to completely remove this layer without causing any damage to the underneath layer. And then next one is exposed. And I can repeat it as much as I want, basically as many layers I have. And here are the results. And I would like to show you for MOCVD boron nitride grown in different conditions. So first, when we consider the different carrier gas, you can see that when we compare the boron distribution or carbon distribution within a layer, there is a significant differences. So first of all, the boron distribution is very inhomogeneous if argon was used as a carrier gas, and there are even some places where there are no boron nor nitrogen actually can be detected. On the other hand, for hydrogen, the very same material is very homogeneous, very nicely distributed boron. When we switch to carbon analysis, we can see that there is a lot of carbon. I would like to emphasize that in here, the average counts for carbon dropped from 1000 to just 11 when we switch the carrier gas. And similarly, there was much higher boron counts for this sample than for this one. So this means it can be estimated that there is about 10% of carbon within this sample grown in argon, whereas just traces like ppm regime carbon for sample grown in hydrogen. But what is quite interesting in here that we also see that in the same places where there is no boron or nitrogen, we can see the carbon precipitates in here. And that gave us idea that obviously this sample grown in hydrogen is of much higher quality and in general of much better applications. But these carbon precipitations are very nice markers to study the growth process again with SIMS. So we also this time we switched to argon to see these precipitates, but we did it for different reactor pressure. So when we did it for the high reactor pressure, this is a so-called self-terminated growth mode. You can only grow 6 layers of boron nitride in this mode. This is, as it is its name, self-terminating after that. Nobody exactly knows why, but here's a very nice results that when we analyze this carbon precipitates in here, we can see some animation. As you can see, I mark with a different colors carbon precipitation present in different layers. There are exactly 6 layers, as you can see here. But as you can see, there is absolutely no correlation between the position of this carbon precipitates in one layer and in the other. So they are randomly distributed. On the other hand, for a low reactor pressure on the right-hand side, first of all, we can grow as many boron nitride layers as we want. So here is 66, I think, layers. But more importantly, you can see that the correlation of the position of one precipitates in one layer to underneath layers is very good. So here we can see some kind of a pillar-shaped structures of carbon. So there is a pretty strong differences in these two growth modes. So we made a conclusion about it. So basically in this three-dimensional mode, for the low reactor pressure, the average diffusion length of precursors of either boron or nitrogen or carbon are long enough so they can always attach to a preferred site. So whenever the reaction takes place, they will simply find a suitable location to get attached to. However, in the self-terminated mode for high reactor pressure, this is not the case anymore, and the average diffusion length is severely limited, and thus this atoms has to get attached to the growing film wherever the reactor took place. So that is why there is absolutely no correlation of position of carbon precipitates. So as I said, I really enjoyed this experiment, and luckily it was not only me who really thought that this is worthwhile, and the graphic presenting the idea of this experiment was on the cover of Journal of Analytical Atomic Spectrometry, where the suitable paper was published. Okay, so now there is also a question. I showed you how I can remove the top layer without damaging the second one. So the question was, how does it work? And for that, I cooperated with my friends from Krakow, which makes the computer simulation. And they said that basically from their simulation, it turned out that for a sample which is perfect hexagonal boron nitride layer for experiments with such high incident angle that was, I think, 70 degrees. Their simulations showed that all projectiles are simply reflected from the surface, and there is no sputtering process at all. So to study it more, they also in their simulations included a large circular defect, as you can see from the top view here. And then the bombardment, the cesium bombardment is coming from left side to right. And here you can see the simulation that the bottom layer is not affected at all, but the top layer is sputtered, but in a very asymmetric way. As you can see, with the direction of the primary ions, it's much faster than any other directions. And obviously, this is to expected that no real sample is perfect. We still have some vacancies in the real sample, so that is how the sputtering process can generate. However, from this simulation, this anisotropy is something that I really thought about, and I thought maybe we can repeat this experiment. Show this anisotropy of the sputtering process experimentally. So I designed additional experiments. So basically, I took this. This is also 6 layers of boron nitride grown on sapphire. So instead of measuring boron or nitrogen or carbon, I measured aluminum. So this is the signal which will show that all the layers were completely removed and the substrate is exposed. So this is shown here. But first, for a very small region, I pre-bombarded it with high energy ion beam, but with an extremely low intensity. So I introduced a lot of defects in this area, but I did not sputter it yet. So then when I start such experiment, at the beginning, there is absolutely nothing. After 4 seconds, I expose this region, but then when bombarded from left to right again, I see exactly the same effect. So if I run it again, you can see that the sputtering process is once again proven experimentally anisotropic, and it's much faster in the direction of incident than any other directions. So basically this way we proved how does it work that you can sputter one layer without causing any damage to the bottom one. Okay, but also we made additional analysis about the contamination in this layer, particularly in case of the aluminum. This is one of these preliminary results that I still need to work. As you can see, for each boron nitride layer, I see some drop of the intensity. But once again, you can see exactly 6 boron nitride layers. But what was also important that we see some aluminum peak residing exactly between the layers, and at the same time, whereas the boron nitride has a clear decreases here, the nitrogen, okay, this is not perfect, this is still some kind of noisy. There are some decreases in the first layers, but then later on when we see this aluminum peaks, this decrease is not such well pronounced as here. So we expect to prove that actually during the growth process, some small crystals of aluminum nitride are residing between the boron nitride layers. So in here you can see that the actual depth resolution is really extreme, because this is a single atom thick layer, and we can also detect some traces of elements which are between these layers. But as I said, this still requires additional work. Okay, now let's change to much thicker sample. In this case of the gallium nitride, this is a very sophisticated procedure. I spent a lot of time to develop it. So basically what I wanted to see is to check the unintentional distribution of oxygen contaminant in gallium nitride material. So this is the result, and you may see, okay, you said something that you spend a lot of time, but there is nothing special about it. So basically, you see a very random distribution of oxygen counts in this sample. But the problem is that the oxygen is also present in the analysis chamber of SIMS, and we get the background contribution. So this is most of this, and I estimated that about 95% of the voxels that you see here are not actually coming from the sample itself, but from the analysis chamber. So this does not, they do not represent the actual oxygen distribution in the sample. But since their detection from the this background contribution is completely random, I assume that we may use this randomness to our advantage and basically reverse it. So after obtaining this result, I propose to randomly eliminate 95% of the voxels of these oxygen counts from this result. And this is what happened during this reduction analysis. So as you can see, when we start to eliminate 95% of them, it turns out that the oxygen is not uniformly distributed as it may seem at the beginning. But once again, we can see a very clear pillar-like structures. So the oxygen is agglomerated along some very narrow lines. And in here, we combine the SIMS analysis with SEM pictures. So, and then we superimposed the SIMS results. So this is this blue pixels on the chemically etched gallium nitride material. And this etching is actually revealing the position and type of dislocations in this material. So this biggest pits represent the screw or mixed dislocations, whereas the small pits represents edge dislocations. And as you can see, these pillar-shaped structures are always located along the core of the biggest pits, which represents the screw and mixed dislocations. There are some kind of a type of dislocations that still there are clearly screw dislocations, but there is no oxygen in them. So we assume that these samples have a closed core, whereas the other ones have an open core, and that's why we can see this agglomeration. So basically, the oxygen is not uniformly, this unintentionally introduced oxygen is not uniformly distributed, but it has a strong tendency to decorate this screw or mixed dislocations. Okay, staying with the nitride materials, I also made the analysis of indium gallium nitride quantum wells, and particularly the important challenge to make such a laser diode with such quantum wells is that the p-type material, which is grown on top of the sample, usually requires much higher growth temperature than the indium gallium nitride materials. And the other problem is that there is a huge lattice mismatch between gallium nitride and indium nitride. And that means that usually it's assumed that the indium distribution within this quantum wells, there are quite a lot of fluctuations. And from electrical and optical measurements, it's turned out that this growth temperature has a huge impact on the performance of such a structure. So if the temperature is low, the actual optical power is also very low and with the high wavelength. But then when we start to increase the temperature, we can see that the situation is getting better with much higher optical power. But then after some time, we can see a very sudden drop. So we want to study it with SIMS, but once again, there is a little problem because the typical standard SIMS produce the depth profile, starting with the depth profile, produce such an image, but this is not very good because there is just a few data points. You can see a Gaussian-shaped feature, but then I use this ultra low impact energy SIMS. So I reduced the energy, increased the incident angle, and made a procedure that can make such a depth profile much better, which is presented here. Now you can see that these quantum wells are not registered as like Gaussian-shaped peaks, but really box-like structures, which is what it's supposed to be. So with an extreme depth resolution in here. And having such a picture, such a nice depth resolution, we can also introduce the lateral imaging, so and actually three-dimensional ones. So here's the results when I present the indium concentration for various growth temperatures. Please note that this is not a TM image. This is still a cross-sectional SIMS image. So here there is 200 microns, whereas in these directions there is just 30 nanometers. But first you can see that these quantum wells, indeed, there are huge indium fluctuations within these layers. So the differences can be as high as 10% of indium. There are some regions where there is rich in indium and other where are very poor in indium. At the same time, I made the additional analysis of nitrogen distribution in the same region, and for this temperature you can see that there is absolutely nothing interesting homogeneous distribution. However, when we increase the temperature, we see the homogenization of this indium distribution within this quantum wells, and that's why the quality of the optical power was much higher and much better controlled the wavelength emission. However, we see that from the bottom layer, so the first one which was grown, there is some kind of an indium precipitation, which is also noted by the corresponding decrease of nitrogen in here. So we can expect to see some metallic indium starting to precipitate from this region. There is not so many regions where such a precipitations can be found in this temperature. That's why the operation in this temperature was very good. But for the highest temperature, when there was also this sudden drop of the performance of this device, we see such a image. So the bottom layer was completely decomposed, as you can see. So there is quite a lot of indium precipitations, but also there are some regions where some agglomeration of nitrogen can be found. So we interpreted this some kind of a nitrogen bubble forming within the void of this material. And also what is quite interesting to see is that this decomposition only affects the bottom interface, not the top one, which was also confirmed by TM images. And then we can see the already precipitation of the second quantum well here. So the interpretation was that, okay, we can really see the microscopic fluctuation of this indium precipitation. There is, we can see this metallic indium precipitations. Nitrogen bubbles, we can confirm that only the bottom interface is affected. And the current explanation is that during this growth, there is a huge out-diffusion of vacancies from the lower regions towards the surface, and this is causing these precipitations and decomposition of quantum wells. Okay, staying with the optical devices, now I would like to show you the analysis of vertical cavity surface emitting laser. So this is a very complicated structure and very difficult to be analyzed with SIMS. Basically because it consists of this Bragg distributed reflectors, which are consist of hundreds of layers with the graded composition and a very thin quantum well region. So basically when you use standard SIMS, this is already quite nice result, but you can see that first of all, these layers, the thickness of them should be identical, whereas it seems that they are getting thicker and thicker when the depth profiling progress. And also, we do not really see any well-defined quantum wells here. There should be 5 of them in here. We can see the indium signal blurred. The problem is the aforementioned mixing effect, causing that for such a thick sample, like 8 microns, the roughness of the crater is also playing an important role. And there is a primary beam deterioration because such an analysis is very long. So I will not maybe explain in detail everything about the procedure that I made, but I'll mention that I made an additional, very enhanced procedure where I was also polishing this from time to time, the crater, to decrease the roughness, used a very low impact energy and high incident angle to decrease the mixing effect. And when I was also polishing it, just a little bit, the sample, I was also making sure that the primary beam condition stays in shape. And then finally, the result is presented here. So now, as you can see, this is a very high quality result. All the layers are represented with a very high precision. We can also include gallium signal here. We can also include the dopants and contaminations in oxygen. So we can see the carbon p-type dopant and n-type dopant. And we zoom in into the quantum well region. We can see a perfect separation of 5 quantum wells. So this is also, I spent quite a lot of time to obtain the procedure, but the mixing effect was eliminated. The crater roughness was eliminated. Now we can have a very good depth resolution, high quality results, including the dopants. So this was a very, very good achievement. And now let's switch back a little bit to two-dimensional material in terms of molybdenum disulfide. So we made a very simple process how to produce this material. So first, we simply sputtered some molybdenum on a substrate. And then we use a high temperature sulfurization process to obtain molybdenum sulfide. But then from SIMS, it turns out that the type of a substrate has a huge impact on the quality of the material. Okay, so switching back to 2D materials. So we made a simple process to grow 2D materials. So basically, first we have operated some molybdenum on a substrate. And then we use the high temperature sulfurization process to obtain the MOS2. Then SIMS revealed that there is a huge difference in quality of the materials depending on the type of a substrate we used. So when it was silicon dioxide, we see we made the first, based on the reference sample, we made that when for the molybdenum to sulfur signals ratio of about 4.4, a little bit below, so represents in green, this is a high quality, high stoichiometry MOS2. Everything else is not. So first, you can see that for silicon oxide, we can see some triangular shaped regions where there is a high quality MOS2, whereas for sapphire, these regions, these domains with a high quality materials are much, much higher. However, in both cases, there are also regions where the stoichiometry is significantly alerted. And we also included the oxygen analysis shown below. And here you can see that we cannot detect any oxygen in the positions where the high quality material is present, but there is a lot of oxygen everywhere else. Profile actually, we showed that there is a clear oxygen release from the substrate which contain oxygen, as you can see here when compared to the normal substrate without the molybdenum disulfide film. And thus the oxygen can diffuse into the layer, and that's why the quality of the material is not perfect. So basically, that's why we grew only a small part was a high quality film, where anything else was highly oxidized with an unknown stoichiometry. The solution to it was to either use a substrate which does not contain any oxygen, so we did it for boron nitride, or later on we simply optimized the procedure with the lower temperature process. And in both cases, we were able to obtain high quality material. However, the most interesting part was when we tried to repeat the same experiment to make the molybdenum sulfide film on top of a graphene which was CVD grown on silicon carbide. We grew it on top of graphene, and to our surprise, the result was that, as you can see on the depth profile, that actually the molybdenum sulfide film was formed below graphene. This was kind of surprising, but we assume that the explanation is that the silicon carbide has the step edges structures with some edges and terraces, and it is well known that at the step edges some material can intercalate the graphene. So we repeat the measurements only with molybdenum, and so we deposited some molybdenum on graphene and heated up, and we saw that the molybdenum at the very top, at the surface, there is some depletion of molybdenum corresponding exactly to the step edges of silicon carbide. And when we made the same molybdenum image with SIMS below graphene, after sputtering graphene, so at the interface with the silicon carbide, we see also that this molybdenum indeed intercalated graphene in these regions. But here, where the depletion was directly, as you can see, was symmetrical, the molybdenum that we find on the silicon carbide interface is not symmetrical at all, but you can see here is the line scan, so there is a very sharp interface in one case and a clear diffusion in the other. That simply means that this step here is higher than this one, so when the molybdenum is intercalating here, it can only diffuse along the terrace in this direction. But again, the final result is that actually in this case we can grow the molybdenum sulfide film below graphene layer, which was kind of surprising. Then I also wanted to show you the organic materials analysis. This is a very recent result. So magnetic sector SIMS is typically not well used for such a materials. Usually you use TOF SIMS, but we made quite an interesting experiments using this high incident angle bombardment and ultra low impact energy. Here, this is the standard result. This is a mass spectrum of organic molecules. This is a terperidine with iron. And what you can see here, that for a standard, we can see a lot of various peaks. And important thing is that this mass spectrum is very difficult to interpret, because we not only see fragments of these molecules, but we also see some mixed fragments. And when we switch back to very low impact energy, we only see some specific fragments, which all of them we can identify. And the important part here is that this particular result is 150 eV, but when we start to decrease the energy, some of these fragments start to disappear. So then in the end, we can only detect one peak, which means that with the decreasing of these energies, we can also probe how these fragments are formed. So which bonds within this organic molecule, how strong they are, in which order they will be destroyed. This is a very preliminary result, and we still want to use it, but we need to optimize it, definitely. We will use it for the identification of organic materials, but also with the bond strength. We have plans to introduce some mapping of the materials. Perhaps the isomers identification will be possible, maybe even depth profiling of organic materials, and who knows what else. The last example I would like to show you, because this is a very good summary of my work, is the very first publication that I made in 2016. Actually, I made this research in 2015 when the instrument was freshly installed in the institute. This is a case of a graphene on silicon carbide capped with chromium layer. And on this result, published in Applied Physics Letters, we showed that we can see the because the hydrogen intercalation in this process, we can see graphene where the carbon signal starts to increase and silicon signal is not yet increasing. It's a little bit later. So it's the carbon is on the between the graphene is between the dashed lines, and we can see some organic contamination staying in this chromium capping layer and maybe diffusing, maybe penetrating the graphene. It was not really very clear. But then exactly 5 years later, I repeated the same measurement, but with much higher knowledge, and after accomplishing all the data that you've seen before. So I knew that I can make the analysis better, because I got better with this tool. I understood how to work with it. So I repeated the measurements on exactly the very same sample, and the result is shown here. So now the dashed lines are actually not needed anymore. You can really see from the carbon signal changes. It's a little bit, the intensity is a little bit changed to match, to better show the result, but nevertheless, the result is much better. Now you can see that this organic contamination do not penetrate graphene. We can already see this hydrogen intercalation, but which is also very nice to see it here, because this is actually a bilayer graphene, that we can see some hydrogen molecules trapped between graphene layers. So with such a precision, we also and try to use it for detection of contaminants, and also compare the standard one. This is graphene grown on germanium, where we can, here was the case was that the reactor itself was a little bit contaminated because other materials were used. So here it's really difficult. Okay, in carbon, we can see that the carbon is decreasing, so probably graphene is somewhere here. Here the germanium is increasing. All of these contaminants can be detected, but not much can be said where precisely they are located. But again, with the enhanced results, we can do it. There is a very clear difference between graphene, so the carbon signals decreases, germanium increases. And now we can see a very interesting thing, that on the very surface of this material, we can find sulfur and sodium, probably from simply from air. The copper actually is introduced into the graphene layer, so forming the copper graphene composite, whereas the molybdenum and tungsten are located at the interface between graphene and germanium substrate, and also some additional surfaces penetrating the germanium, which is not surprising since sulfur is passivating the germanium surface. So that basically shows that after these 5 years, the precision of graphene depth profiling has been significantly increased. Okay, so just a short conclusions about my talk. So I showed you the well, I can say state-of-the-art instrument, which allows to use the very low impact energy and manipulate the incident, combined with the dedicated procedures that I try to develop, which are very time-consuming, but as you can see, worth it. It is indeed possible to analyze 2D materials and also other materials with very good resolution, very often sub-nanometer depth resolutions. And as I said, the procedures are all, I try to improve them all the time. And so some of the results were still not perfect, but okay, I would like to say that I'm working on them right now, but I'm not, because due to the pandemic situation, I'm not allowed to be in the lab for some time now. But hopefully it will change soon, and I will also work with this procedure. And the last part, I wanted to also mention that if you have any interest in such analysis with such a precision, I'm very open for any cooperation. And with that, I would like to conclude my talk. Thank you for your attention, and sorry for these technical problems.
Thank you very much, Pawel. And I'll now ask everyone, if you have questions, just unmute yourself and you can ask your questions now.
Maybe I can start. Thank you very much for a nice presentation. It looks like that you have solved all the SIMS problems like graphening, mixing, and etc. So my question is, if you could a little bit more specific regarding the energy which you use for the sputtering and polishing, or if the energy is the same, because as it's known, once you reduce energy, you also reduce the sputtering coefficient, and you have shown us quite let's say profiles with I would say hundreds nanometers or something like that. So what energy you use for the sputtering, if you could be more specific regarding the X-ray mirrors and things like that.
Sure. Okay, maybe I will show a few things. So I will start with this one. The left profile, pretty often the drawback of this procedure is the analysis time. The left profile, it took 5 minutes to get it, and the right one is 3 hours. Roughly the same depth. Okay, the depth calibration is just for estimation. So in here, I sputtered 6 nanometers for 5 minutes, and here 6 nanometers for 3 hours. So the difference is huge. So basically the integration time of these signals is much higher than in the other ones. So that's for graphene. And in here, yeah, that was the problem, that actually I wanted to show more examples without going into too many details. But in this case, yeah, there are a lot of things happening here. So what I basically did was that the sputtering was with, I think, the 250 EV for most of the DBRs. But when I reached the region close to the quantum wells, I used 100 EV to obtain the very good depth resolution. So I also changed the impact energy in between. Whereas the polishing itself, it worked a little bit differently, because I used relatively high energy, that was 2.5 kV. But this was with the extreme incident angle that was well above 70 degrees. And I also applied some additional voltage to the sample. So these ions could not actually hit the surface of the sample. They were just like sliding at the very top, just above the surface of the sample. So whenever they reached something, some leftover contaminant, they polish it and remove it. So the polishing was used with much higher energy, but with this additional voltage to prevent the sputtering of the surface. So this was just for the making the surface very flat. And then I just use it for a few seconds every half an hour or something like this.
May I? So you use the same ion gun for that, and you are changing the angle of sputtering, or you have some additional?
This is the same. Everything here is done with cesium gun.
So you are changing the angle during the analysis.
Yes.
Right.
And angle, I'm changing the incident angle, and what's even more funny, I'm also changing the polarity during the analysis. So the software I'm using does not really allow to do it, but with a simple scripts, you can do it. You can automate it. So this profiles, it took like, I think 20 hours to obtain, something like this, but this was fully automated. So it was really a lot of time to make such a procedure with all these changes of the primary energy, current, with polarity change, even with inclusion of this polishing, so to say, service moments where I was at the same time readjusting the primary beam and also polishing the material itself.
Interesting. Thank you for information.
You're welcome.
If nobody else is asking, maybe one have another question. And what about the lateral resolution? You have shown some precipitates in indium layers. It looks that even lateral resolution is quite good.
It's not.
Not?
No, not that good. I would say that this is 1 micron. The lateral resolution. So here it is. Okay, this is the very good example to show it. Okay, sometimes it can be a little bit better, but as you can see, the oxygen is probably located in the cores. And as you can see that these regions are actually rectangular every time. This is because the secondary image inherited the shape of the primary image. So the problem is that when you form the image with, deform the beam with these mechanical parts, these square stencils, you can do only so much how you can decrease the size of it. So slightly below 1 micron is typically the best you can get. And in here, for example, this precipitates, I actually don't expect this precipitate to be 20 micron thick. I think there are some agglomeration of smaller precipitates here, but they are blurred together. So I would say that I can't complain, because without the square stencils, I wouldn't reach such a good depth resolution, because as I said, you really need a homogeneous beam. But the actual primary, the lateral resolution is, okay, maybe it's not exactly 1 micron, maybe it's a little bit better, but definitely in this regime. So it's definitely not something like 50 or 100 nanometers.
And what's the beam diameter? Is it limited by the beam diameter or by something else, the lateral resolution?
Yeah, I would say mostly by the size of the beam.
So you have the beam of 6 electron volts the beam width, it's like 1 micrometer, something like that.
Yes, can be done. But it's also very difficult to optimize, especially at the beginning.
Yeah.
Because basically it actually requires really a lot of time, because to be sure that this beam is so small and still homogeneous, I was using it that I was recording a lot of parameters to go back with, and I made craters with these different sets of parameters, and then I was removing the sample and checking with AFM whether the crater is flat or not. So the first step to optimize, it really took me like, I don't know, 2 or 3 months to do it. But then with changing these parameters, I started to know which parameters are actually very important and which not so much. And with this knowledge, I was finally able to optimize it.
I saw your presentation in Kyoto, I guess, and all participants were surprised what SIMS can reach. So congratulations and thanks.
Thank you. Yeah, that was the results that you see on the screen.
Yeah. Thanks.
Thank you very much. Any more questions?
Yes, hello. I'm curious about how did you achieve the rectangular shaped beam as you showed in the beginning of the presentation?
This is the enhancements of the tool itself. So they basically, this is the CAMECA instrument, and this SC Ultra or WF. This is basically the same type of an instrument, just with a different sample holder. So this is not something that I made myself. This is the manufacturer of the instrument made this invention. So this basically, the principle is very simple. There are 2 square stencil made out of tungsten, and when you project, so you basically, when you deflect the beam, you project them on a small square hole. So then it simply cut off the rest of the beam and only goes through the rectangular spot. And obviously, after some time, you need to replace these stencils because they're constantly being sputtered. So after some time, their quality is is getting worse.
Oh, okay, thank you.
No more questions, apparently. Maybe I'll show myself again.
I'll do too. So, okay, then there are no more questions, then I will once again thank you, Pawel. It was great having you here, and the presentation indeed was very nice. And apologize once again for the technical problems. There's always something.
Yeah. Yeah, but we can't do it otherwise in this time.
Okay. So thank you everyone for attending and have a very nice day.